Welcome to chapter 10. In this chapter, we'll discuss the memory system. So, up till now, we have been very vague about the memories that are used in a typical processor system. So, in this chapter, we'll look into this in great detail. This is again the 10th chapter of the book Computer Organization and Architecture. It has been published by McGraw-Hill in 2015, and you will get copies of this book in almost all the countries via Amazon. If there is any problem with the availability, you can kindly send the author or the publisher an email. So we will discuss this chapter. We'll discuss 4 separate sections. One is an overview of the memory system. Then we'll discuss caches. We'll then go into the details of a memory system, look at mathematical models, and finally discuss something called virtual memory. So up till now, we have assumed that the memory is one large array of bytes. Sorry about that. Yeah, we have assumed that the memory is one large array of bytes. This large array starts at 0 and ends at 2 to the power 32 minus 1 if we assume we have a 32-bit memory system. So every program will perceive the memory as one huge array of bytes. For each of these is 1 byte, and each byte has an address, and that's the memory address. So we have also assumed that it takes 1 cycle to access the memory, which means perform a read or write. So this is the assumption that we have been making, that when we write a program, an assembly program to be specific, the entire memory in the system is assumed to belong to that program, and the program can write to any part of the memory space at will. So that is not what happens in reality. What happens in reality is something like this. We have many programs running at the same time, and we have to somehow magically avoid overlaps between programs running on the same processors, right? And running on the same processor. Also, what we have assumed is that all our programs require less than 4 GB of space, which again, might not be true. So, for example, let's say we have a processor. So we have a processor over here. And the memory might be 1 GB, 1 gigabyte. So in this case, we'll have to live with this limitation. So all our programs still need to run over here. And it is also possible that one of our programs, we can have, let's say, 64-bit addressing. And it's possible that we have a program that requires 8 GB of space. And we have 1 GB of physical memory. So how would we run such kind of a system? This is what we will discuss in the latter half of this chapter, when we'll discuss virtual memory. So let me try to motivate this as follows. So we have essentially made 2 assumptions. One assumption that we have made is that one program, one running program, in a sense owns the entire memory system. So that is one first assumption that we made, that the entire memory system belongs to one program, right? So basically that's the first one. The other assumption that we have made is that for a 32-bit memory system, the physical memory is 4 gigabytes. That need not be the case. So we can have a small physical memory, for example. So we can have maybe a 1 gigabyte physical memory. And then, we need to see how to run a program on such kind of a system. So let's first take a look at the the assumption number one. So this is a screen capture of the Windows Task Manager. So the Windows Task Manager shows all the programs that are running on my system at this very point of time. And as you can see, I'm running Skype, which is taking 89 megabytes of memory. I'm running PowerPoint, which is taking around 79.8 megabytes of memory. Then I'm running many more programs. As you can see, if I just scroll down, I'm maybe running 100 odd programs. Sorry, I'm running 74. I'm running 74 programs. So a process is actually a running instance of a program. So I'm running 74 processes. So it is not that my CPU is running all 74 at the same time. It is, of course, it runs one program at a time, but it'll switch between programs periodically. So let's say, it is running program number one, then the CPU will switch and it will run program number two. Then it will switch and it will run program number three. So it periodically switches, right, between programs, and then again it can, again switch back. So when I'm running all of these programs and each program is assuming that the entire memory space belongs to it, there is a possibility of an overlap in the sense that one program writes to one memory address, another program mistakenly writes to the same memory address, so we have an overlap. So this is something that should be avoided. But the most important point that should come out from this slide is that at any point in a system, multiple programs are running, are alive at the same time. But of course, a given processor, so let's say there is one processor can only run one program at one time, right? So if it is running, only way of running multiple programs is that it runs one program, and after some time, it again switches and it runs one more program, right? Again, so it sort of switches between the multiple programs. But even if it switches, we have to ensure that if one program has written to, so let's assume that this is the memory space that we have. If one program has written to these regions of the memory space, then the next program does not touch these spaces. Otherwise, there'll be a problem. So we need to solve this. Also, we have been making some more assumptions. We have been assuming that the entire memory, takes the same time. It takes one cycle to access any part of the memory system. So that's not correct. So let's take a look at the different kind of technologies that we have learned, which can actually be used to make a memory system. So one is a master-slave D flip-flop that we talked about. So its area, typically is very large. So it's around 0.8 micron square. So it's a fairly large structure, but it's fairly large and it's fairly fast as well. So in a fraction of a clock cycle, it's possible to access the flip-flop and also do more work. In contrast, if I consider an SRAM cell, in a cache or in, so I should rather make it in an array of SRAM cells. So if I consider a single SRAM cell in an array for storing a single bit, it is actually 10 times more area efficient. So the area that it takes is around 0.08 micron square, and the typical latency will be 1 to 5 clock cycles. If I consider a DRAM cell in an array, so it is even more area efficient, right? So it is even 16 times more area efficient than an SRAM cell. So it only takes 0.005 micron square. So these are slightly old values, but the ratios will still remain the same if I consider current technology. So a DRAM cell would take something similar, 0.005 micron square, and the typical latency, however, for accessing a DRAM array is very high. It's around 50 to 200 cycles. As we can see that DRAM is the slowest. and the D flip-flop is the fastest. Right? But well, speed comes at a price, and the price is area efficiency, and this is sort of at the middle. Right? So SRAM is in the middle, but as we see that as we increase the area, and increased area also means increased power, the latency decreases, so our cells are faster. And similarly, when we go and we used a DRAM cell, the area is uh, very small, but the latency is high. So all of these things you can again go back to chapter number 6 on memories and DRAM cells and SRAM cells. So if just in case some of you have forgotten, you can go back to chapter 6 and take a look at it once again. So just to refresh your memory, a DRAM cell is actually a single capacitor. A SRAM cell is a cross-coupled inverter. And a master slave D flip-flop, well, that essentially consists of cross-coupled NAND gates. Two of these. So basically one of this and one more with some additional complexities. So this is there in chapter 6, but the basic idea is that a certain trade-off exists between latency and area. So should we make our memory only using flip-flops? Well, it's a very bad idea, because for a given amount of chip area, we'll be able to fit only very few bits. In contrast, right, so it's 10 times the area of a memory with SRAM cells roughly, and 160 times the area of a memory with DRAM cells. So these are representative numbers, and also they will consume significantly more power. So we can't use any single technology to make the memory, right? That's the most important take-home point that is coming from this slide. That to make a memory system, so there are trade-offs. Maybe I can write down. So there are area versus latency trade-offs. So as the area increases, the latency decreases. And similarly, the power versus latency trade-off as well. So as the power increases, as we have more power, the latency decreases. However, the entire memory cannot be made of just flip-flop cells. It'll not contain, its capacity will be very low. It'll not be power efficient. It'll consume too much of power. Similarly, the entire memory cannot be made just of DRAM cells, because we can fit in a lot of bits, but it'll be too slow. So, given these things, we can nicely summarize all the trade-offs over here, something that we discussed in the previous slide. If I increase the area, I'll reduce the latency, of course, but increase the power. If I make the memory cells faster, I'll increase the area, but I'll increase the power as well. And if I reduce the power, well, I have to make them smaller and make them slower as well. So you cannot have the best of all worlds. So it's a philosophical thing, but that is true, that having the best of all worlds is not possible, right? That is simply not possible. So what is, in a sense, desirable is that we have something, some kind of a solution which is a compromise. So, as we have been discussing, having a memory with just flip-flops will not be able to store anything. With just SRAM cells, well, we need more storage, and that also will not do. And with DRAM cells, we'll have a lot of storage space, but every access will be very, very slow. So what do we do? So memory latency depends on, well, the size of the memory, yes. The larger is the size, slower it is. The memory access latency also depends on the number of ports. So this is, let me discuss this. See, consider a small memory like a register file. So in the register file, there is one instruction which is reading in one cycle, and there's also one instruction which is writing. So if the instruction is reading two registers in the same cycle, you need two read ports or two interfaces to read. Similarly, one instruction is writing, you need one write port. A port is essentially an interface to write. So two read and one write. Right? So we can always have a slightly bigger, we can always have a different kind of processor that instead of one instruction issues two instructions per cycle. So what would this processor require? It would need 4 read ports and 2 write ports. 6 ports, right? So we have one more, so more are the number of ports, the number of parallel accesses per cycle. Slower will be the memory, and slower also will be, more will be the power. And then the latency also depends on what kind of technology we use. If it's a SRAM or a DRAM or a flip-flop, it'll take different amounts of power and latency and area, as we have discussed, right? So what are the main things that are in our control? One is the size, right? So we can tweak with the size of the memory. So if, let's say, the storage capacity is low, so if it's a 4 kilobyte memory, it'll be very fast. If it's a 4 megabyte memory, it'll be fairly slow. And the number of parallel accesses we are supporting, right? The number of ports and the technology that we are using. What are we building it with? SRAMs or DRAMs or flip-flops? So let's look at a solution, but let's first search for a solution in real life. So let's leverage some patterns. So let us consider a student Sophia's workplace. So let's assume that Sophia is sitting over here, right, on a desk. And she has some books on the desk, and nearby she has a shelf which has some more books. And there is a cabinet, there is a huge cabinet that is far away, right? So clearly the desk is small. So if in terms of size, the desk is the smallest, and this is smaller than the shelf. Which is smaller than the cabinet. Right? So the cabinet is huge. Cabinet is huge, it's far away. So what is one thing that we can see from here? Accessing a book from the desk is fast and quick, but the desk also has small size. Then we have the shelf, which is slightly larger, and it can fit more books. And then we have the cabinet, which is really large. So what would be the right way for Sophia to organize her books? The right way will be for Sophia to keep the most frequently accessed books on her desk, right? So the books that she is reading. For example, if she is preparing for an exam, she can keep the books that are the most related to her course, to her exam, on her desk. She can keep the slightly less frequently accessed books on the shelf. Right? Some books, some reference books can be kept on the shelf, which are not used all the time, but can be used sometime. And the rarely accessed books, which she hardly ever reads, there'll be many, many such books, and they can be kept in the cabinet. Right? So we can have, so what is most important is we need to note these 3 words: a desk, a shelf, and a cabinet. A desk is small, and so essentially a desk is small and fast. So what this means is that you can get a book from the desk very quickly. In contrast, a cabinet is large and slow. So it takes a lot of time to actually find a book inside a cabinet because it's large. And so that's the reason it's large and slow, but it has more capacity. And a shelf is somewhere in the middle. So if I'll just look at size, so basically I just can write it once again that a desk is smaller than a shelf. is smaller than a cabinet. If I look at latency, or time it takes to get a book, fetch a book, then it's the reverse. A desk is faster than getting a book from a shelf, which in turn it is faster to get a book from the cabinet. So, why does this strategy make sense? Well, the strategy makes sense mainly because of the nature of human behavior, right? So let's say before preparing for an exam, she will tend to read the books which are on the desk more and more, right? Over and over again, she'll read the same books because she's preparing for one exam. And so in the same window of time, which is maybe a day or 2 or 3 days before an exam, a certain set of books will be accessed. After that, if there is another exam, one more set of books will be accessed. So any kind of such a pattern is called temporal locality. Temporal means time, it's the adjective form of time. So in a short duration of time, when we access the same thing over and over again, that's called temporal locality. In this case, before an exam, the same books will be accessed over and over again. Because of the phenomenon of temporal locality, it makes sense to have a small desk where we can keep our books. So most of the time, maybe 90% of the time, we'll get the books from the desk. Then again, it makes sense to have a shelf. And out of the remaining 10%, right, maybe 9% of the time, we can get the books from the shelf because the shelf is larger. And then again, we can have a large cabinet where the remaining 1% of the time we need to go. So the advantage of this particular organization is that 9 in 10 times we can get the book within arm's reach. Out of that, 9 in 100 times we can get the book from the shelf. So maybe Sophia just needs to walk 10 steps. And only 1 in 100 times does she actually have to make a trip to the cabinet which is at the end of the room. Which sounds reasonable. This is typically the way that we organize things. So even on a kitchen, this is exactly what we do. On a kitchen countertop, we have very commonly used ingredients, right? For example, salt, sugar, that's there on the countertop. Then we have a small shelf, or we have a refrigerator which contains other items which cannot be kept on the countertop because of space. So that includes vegetables and meat. And then we might have some more items that we use very, very rarely. So in that case, it does not make sense to keep them at home. We can always, if we want to make something that uses a very rare ingredient like saffron maybe, we can go to the market and buy one. So this is similar. So this pattern, so this is again temporal locality in action, where what we are doing is that we are basically looking at all our accesses and trying to derive a pattern out of it. So be it accessing memory or be it anything else, we always have some amount of temporal locality. So now let's look at some other patterns. So let's assume that Sophia was taking a computer architecture course. So she had computer architecture books on her desk. After the course is over, well, the architecture books will go back to the shelf. And then, once the exam is over, what do? You have fun, you go on a vacation. So vacation planning books will now come to the desk. So then, she will study where does she want to go on vacation and then figure out the right vacation destination. So one idea that we can use over here is that, look, we can bring all the vacation planning books that she has in one go. So, for example, if she wants to, let's say, go to Europe, But then she changes her mind and decides that she needs to go to Singapore. So it would not be a good idea to make a separate trip for each and every vacation planning book. So it makes sense that she brings all the vacation planning books in one go. So if she requires one of them, in high likelihood she will require a similar book in the near future. So essentially she will make a trip to the shelf or make a trip to the cabinet and come back with a stack of similar books in one go and put them on the desk. Right? So this is what you would typically do. And even let's say when you are cooking and you decide that you want to cook with some spices, then it makes sense to actually go to the shelf and bring in ginger, garlic, green chilies, everything together. Because most likely, if you have used ginger now, you'll require garlic half a minute later. So why make a separate trip? Just bring all the spices in one go. So this is also one more pattern similar to temporal locality. So this pattern is called spatial locality. So let's now quickly discuss both. So temporal locality means So it's a concept that basically states that if a resource is accessed at some point of time, then most likely it will be accessed again in a short period of time. So we saw that example that when Sophia was preparing for a computer architecture exam, she was accessing the computer architecture books repeatedly over a short period of time. After the exam, she decided to go on vacation. So then she brought all the vacation planning books to her desk. So this pattern is called spatial locality. So it is a concept that states that if a resource is accessed at some point of time, then most likely similar resources will be accessed again in the near future. So we discuss spatial locality in the context of a kitchen. That let's say I am cooking and I decided to make a curry. So then I got some ginger from the shelf, but most likely if I've got some ginger, I'll get some garlic and some chili powder later. So I would rather bring all the spices that I have in one go. So this pattern is called spatial locality because there's a very high likelihood that any cook who has used ginger will also use garlic in a very short interval of time. So let us verify if the programs that we write are similar to our behavior in real life and they also exhibit temporal locality. So let us define the concept of stack distance. So let us have a stack. So recall that a stack is a last in first out structure. So similar to a stack of books or anything. So let's just quickly look at what a stack is. So it's a data structure where we just put in data like this and we can just push data and also we can pop data out, right? So we have also discussed about a stack in chapter 2. So it supports only two operations, push and pop. So let us have a stack of memory addresses. So whenever we access an address, we bring it to the top of the stack. So for example, addresses are accessed in a stack. So so what we do is that let's say we had accessed one address some time ago, so it sort of went down the stack. Whenever we find it, whenever we access it once again, we search for it in the stack, we remove it from its position, and we again put it at the top of the stack. So let's follow this algorithm. So stack distance is defined as the number of entries between the top of the stack and where the address was found. And of course, if you don't find the address in the stack, it is infinity. Alright. So what's the stack distance again? It's the distance from the top of the stack and the position in the stack where the given address was found. And if the address was not found, then the stack distance is infinity. So in a certain sense, this quantifies the reuse of addresses because if the stack distance is low, what it essentially means, so if this is the stack, right? And let's say the stack distance is low. What this essentially means is that almost the similar addresses are being used again and again and again. And this is what it would mean. If it's high, means that addresses are being used in a very random way. So once again, the stack distance is the distance from the top of the stack to the position at which the given memory address was found. And when you find it, you move it and you take it to the top of the stack. So well, we plotted the stack distance for a given benchmark. So almost all workloads have similar profiles. So this was for a set of Perl programs. And so the x-axis is the stack distance and the y-axis is the probability. So it's a probability density function essentially. So we see that the highest probability or the most probable stack distances are pretty much these two, which makes it less than 20. So if I've accessed one address, most likely within the next 20 memory accesses, I'll access it once again. And that's, very significant. And if I just add up the rest, what this basically tells me is that, roughly for, let's see, this is around 27, this is around 17, 44, 54. So roughly for around 60% of the addresses within 50 memory accesses, I'll access it once again. So the stack distance per se is low. And since the stack distance is low, it tells me that there is a certain amount of temporal locality in memory accesses, right? And where does this temporal locality comes from? It comes from the way that we code. So how do we typically code? The way we code is that we write a function, so the function would have some kind of a for loop, which will just run again and again and again. And then it'll have, so basically here a similar set of addresses, or maybe the same set of addresses will be accessed over and over. Then again we'll have another for loop where again the same kind of addresses will be accessed over and over. So this is exactly this pattern of the way that we write programs, where you call similar pieces of code, similar functions, access similar kinds of data over and over in for loops and while loops. This is essentially what gives us temporal locality, and thus we have a small stack distance. So let me just remove the, 1 second, yeah. So most stack distances are fairly low, and this indicates to us that there is a high degree of temporal locality in the set of Perl programs that we consider. But even if we were to plot this graph for other kinds of workloads, we would see similar distributions. So to quantify spatial locality, let us define a term called address distance. So let's do one thing. Let us maintain a sliding window of the last k memory accesses. So which means that the last k memory accesses that a processor saw let us just maintain them, right? The last k accesses. So let us define the address distance as follows. So the ith address distance is the difference in the memory addresses of the ith memory access and the closest address in the set of the last k memory accesses, right? So let's assume if k is equal to 10, I just maintain a window of the last 10 memory accesses. Now let's say I access address number 104. So here there is no 104, but I had, let's say, accessed address 100. So this means that I will choose whichever address is there in the last 10, which is the closest to 104. In this case, if it's 100, I will choose this, and the address distance, the difference between these addresses, the absolute value, or maybe just the difference, and in this case the difference is 4. So this, in a sense, shows the similarity of addresses. It basically tells us that if I was in a certain memory region at a certain point of time, and then I make one more memory access, how far away is it actually, right? So let me now explain the logic of the sliding window. Well, the logic is like this. So how do I write programs? The way I write programs is maybe, I would set the value of some variable. So let's say, okay, let me consider another example which is more apt maybe. So let me consider an array. So let me maybe erase this and start once again. So let me consider an array. One second. Yeah. So let me consider an array here of values. So typically, a program that I write inside a for loop, we pass through the array of values and we do something on them. So we can maybe have something as x is equal to vals I, where I is the loop index, plus some constant, plus something else, plus something else. It doesn't matter. And then I can have some more lines. After that, I'll come to the next iteration of the for loop, increment I, and then access vals I plus 1. So when I access vals I plus 1, I will look at my sliding window of the last k accesses, right? So in the last k accesses, depending on the value of k, if it's well chosen, I'll definitely find vals I in here, and this will be the closest memory address to vals I plus 1. So the difference between the addresses is the size of an integer, which in most systems is 4 bytes. So this will be the closest, so the address distance will be 4. So what this is telling us is that the first thing it's telling us is that in most programs, we typically access similar data, and similar data will be there in structures such as arrays, or can be there in a linked list where the structures are allocated side by side in memory. But most commonly arrays and most commonly variables defined in the same region of an activation block. So they have similar addresses. So when I access variables with similar addresses, like in this case, I'm accessing in one iteration vals I. In the next iteration, I'm accessing vals I plus 1. We will see that a notion of spatial locality is coming, right? So in particular for the vals array, since I'm accessing the elements consecutively, so if I consider, the vals array, I am accessing the elements consecutively. First I access I, then I'm accessing I plus 1, and so on. So this means we are accessing similar items with similar addresses, and so spatial locality is there, but the way we quantify it is slightly tricky. So I cannot compare the address of vals I with the address that I access the last, because there might be several lines before it as well, which might be accessing other addresses. So to sort of not get confused, the way we have defined it is that let me consider a window of the last k addresses and find the closest one. So in this case, when I'm accessing vals I plus 1, I'll find vals I, which will be the closest, and it will tell me that for at least vals I plus 1, the address distance is 4. Similarly, there can be other kinds of accesses in between these lines, and we'll always find that we would have accessed some other data location which is close by in terms of memory addresses. And this is a pattern that we can use. So this is spatial locality. This is a pattern that we can use after quantifying it. So let me quantify, again let me consider a case where k is equal to 10, and let me consider a benchmark, a workload consisting only of Perl programs. And let me plot the address distance. So if I do a probability density function of the address distance, so what I see is that the highest probability is centered around 0. So that's the highest. And if I consider this region, then roughly I have Around yeah, 10 plus 25, 35 plus 15, roughly 50%, more than 50% of the accesses are within an address distance of plus or minus 25 bytes, right? So this is typically the way that programs access. This is because there will be many arrays where I'm accessing the array elements. There will be many local variables. So for example, if I define int, I, j, and k, what most compilers would do is that they will give them consecutive addresses. I starting at one point, j 4 bytes later, k 4 bytes after j. So if I'm accessing j and then I'm accessing I and then I'm accessing k, so it doesn't matter what the order is, but we'll always find that we're accessing similar data. Similarly, if there is an array or there's a string or something, so then we'll also, if we are doing a scan through the array using a for loop, we'll also be accessing similar data. So a notion of spatial locality with a low address distance is there. And so that is why we get this graph. And what we see here is that most accesses, if I compute their address distance, more than 50-60% of the accesses is within plus or minus 25 bytes, right? So that is my first conclusion. And smaller is the address distance, higher is the spatial locality. So what does this mean? This means that, look, if I access something with memory address X, very likely in the near future I'll access something with memory address X plus or minus delta, where delta is a small number, right? So this tells me that this pattern is, this pattern does exist in real world programs, and we should use it in some way. So address distances are typically plus minus 20, plus minus 25. And this tells us that if we access some data in the memory, we'll very likely access some other data where the addresses are very close by. And this is essentially high spatial locality. So let us see how we can exploit temporal locality. The way we can exploit temporal locality is as follows, that instead of, we can have a hierarchy of memories where main memory is the last level. So let me maybe put the processor over here to station it at the right point. So what we can do is we can have a hierarchy of memories. Say L1 cache can be small and fast, similar to the disk. The L2 cache is somewhere in the middle, so it's similar to the shelf. The main memory is large, so it contains almost everything. That's similar to the cabinet, so the main memory is large and slow. So similar to Sophia, what the processor would do is that first it would access the L1 cache and search for data. If it finds it, well and good. Otherwise, so hopefully most of the time, because of temporal locality, 90% of the data will be found in the L1 cache. If it does not find the data in the L1 cache, it will go to the L2 cache, which is larger and slower. If it does not find it there, then the processor will go to the main memory, which is the cabinet. And how do we ensure that the L1 is fast? Well, so we make the L1 small, so we have a reduced capacity. So make it small. Smaller means faster. Also use SRAM cells to build it. Right? Flip-flops are expensive, so let's use small and SRAM cells. So L1 will be able to access within 1 to 2 cycles, and L1 cache is also small, so it's several kilobytes. So let's say 16 kilobyte is a representative figure nowadays. Then the L2 cache we can build with again SRAM cells, but it will be much larger. So it can be somewhere between 256 kilobytes to maybe 4 megabytes. And the main memory can be made with DRAM cells because we need high storage and we don't mind the ultra high latency. So this can be 4 gigabytes, 8 gigabytes, 16 gigabytes, does not matter. Right? So this is how we tie up our processor system with what Sophia was doing. So the same way that she had a desk, a shelf, and a cabinet, we have a hierarchy of memory structures. We have a very small and very fast one, typically 1632 kilobytes, called the L1 cache. Right? A cache means it's a section of the memory. What a cache means is that is a small subset of the overall memory. So it is small. We then have an L2 cache slightly larger, 256 kilobytes to 4 megabytes, again made up of SRAMs. And then we have a DRAM based structure for main memories, right? It is DRAM based. For main memory. So it has 4 gigabytes to 32 gigabytes of memory. So that's a lot of memory space. So this is just a quick summary of what we discussed. L1 cache small and fast, L2 cache in the middle. The main memory is large. So this is a hierarchy of caches. So the main memory will contain values for all the memory locations. So we might relax this thing later, but for the time being, let's take it as a gospel truth that the main memory will contain all the memory locations and the caches will contain a subset of memory locations. So let's assume that in a system there are 2 billion, right? Billion with a B memory locations. So the main memory will contain all of them, but the caches will contain a smaller subset. The L1 cache might contain a few thousand, L2 cache might contain a few million, that way. So let's now discuss the access protocol and also the way that we organize our hierarchy of caches. So typically we consider an inclusive cache hierarchy. So this means that the L1 cache contains a subset of addresses that are there in L2, and the L2 cache contains a subset of addresses that are there in main memory, which contains all the addresses. So explaining in another way, the main memory contains the entire set. So let this be S1, let this be set S2, and let this be the entire set S. So S1 is a subset of S2 and S2 is a subset of S. So this basically means that there will never be any line, any cache, any address, sorry, not a line, an address, which is present in L1 and not present in L2. There will never be any address which is present in L2 and not in the main memory. So that will never be the case. It will always be the case that L1 is a strict subset and L2 is a strict subset of the addresses in the main memory. So this is called inclusive cache hierarchy. In general, it's a good idea to have an inclusive cache hierarchy as opposed to a non-inclusive cache hierarchy, which causes a lot of problems. It's more of a research topic than actually a textbook topic. And the protocol is as follows. We first access the L1 cache. If the memory location is present, we have a cache hit. So we say that the memory location is present, so we can perform the access read or write. So the important term here is a cache hit, which tells us that the memory address, the memory location is there in the cache. Otherwise, we have a cache miss. So if there's a cache miss, means that the address is currently not there. For example, if we access the L1 cache and a certain address is not there, a request now needs to be sent to L2. If L2 has the address, it will fetch it and give it to L1. If L2 does not have the address, then it will send a request to main memory, right, which is made of DRAM cells. And so L1 and L2 are typically within the processor, within the chip, right? So what does the chip contain? Well, the chip will contain the processor, it will contain the L1 and the L2, right? And the main memory is typically outside. It's a separate module which is outside. So if we have a cache miss, so what we need to do is we need to fetch the value from the lower levels of the memory system and populate the cache. And this can be followed recursively, which means if L2 does not have, it can send it to main memory. And main memory will always have the data, right? That's the assumption we have been making. So we need not have two levels. We can have L1, then L2, then L3. So a lot of large processors have an L3 as well. And then they have a main memory. Some process also have an L4, but L4 is very, very rare. L1, L2, L3 is common, or just L1, L2 and main memory is also common. But what is the most important here is to have an inclusive cache hierarchy, where the addresses in L1 are a very strict subset of the addresses in L2, and addresses in L2 are a strict subset of the addresses in main memory. So let's take a look at the advantage of having this kind of an organization. So let us consider that the hit rate in L1 is 95%, which means that for 100 accesses sent to the L1, 95 find their address inside L1, and it takes one cycle. Let's then assume that the L2 hit rate is 60%, and it takes 10 cycles to access the L2. And then it goes to main memory where the hit rate is 100%, and it takes us 300 cycles to go to main memory and get the data back. So in this case, 95% of the memory accesses will take a single cycle. 3% will take that additional 10 cycles, right, to go to L2 and get the data back. And 2% will actually take that additional 300 cycles after accessing L2 to get the data from main memory, right? So this is telling us that look, for most of the time, most of our memory accesses are fast, reasonably fast, both L1 and L2, and a very small percentage of them will actually take 300. So these are very rough, crude numbers. It's not 300 exactly. It's 1 plus 10 plus 300. And but we look at the performance of the memory system in some great detail. That's the reason these numbers are very crude at the moment. But the important point to note is that if you have a hierarchy, most of the accesses will hit at the highest level, which is good because the highest level is the fastest. Then gradually smaller and smaller percentages of accesses will trickle down to the lower levels. So we need to design a system where the least number of accesses actually come down to the lowest possible level. Now so the previous discussion was on exploiting temporal locality. So how do we exploit spatial locality? So well, let's look at the address locality plot. So the plot was over here. The address distances are typically within plus or minus 20 bytes, plus or minus 20, 25 bytes, right? So this means that we have fairly high spatial locality. So let's use this pattern. So since most of the addresses are within a small range, so the idea is that let us group memory addresses into sets of n bytes. Each group is known as a cache line or a cache block. So it's an atomic unit in the sense that we'll treat the entire group as one. And a cache block can typically be 32, 64, or 128 bytes, right? A power of 2. So what is the reason of creating these larger blocks of bytes? The reason is as follows, that once we fetch a block of 32 or 64 bytes, because of a very short address distance, and because of high spatial locality, a lot of accesses in a short time interval will fall within the block, right? So it'll fall within the address range of the block, or a lot of accesses will find their data in the block itself. So consider this once again. So let's assume that there is this address with address 100. And most of the time we are finding, in a short interval of time, most of our accesses will be between 75 and 125. So it's a good idea. It's a very, very good idea that what we do, the same way that Sophia fetched all the vacation planning books at once because she thought if she'll use one, she'll use the other, is that we divide the memory system into 64 byte blocks. So one is address 0 to 63, other is 64 to 127. So this basically means that if let's say we start a program by accessing address 100, in very, very high likelihood we'll be accessing most of the addresses in the range of 75 to 125 as per our plot in a short span of time. And if we fetch the entire 64 bytes together from the lower levels, from the main memory or from the L2 cache into the L1 cache, then uh, we will reduce our miss rate significantly, right? Because of spatial locality, if all the accesses are within this block in a small period of time, we'll all have cache hits. So we'll not have to go outside the L1 cache. So it's a fantastic idea in that sense. So what again is the conclusion from our address distance plots? It was that let us break down our entire memory space that we have into contiguous sets of blocks where a block is 32, 64 or 128 bytes. And let's treat a block as an atomic indivisible unit that we fetch from lower levels or displace to lower levels. And the advantage of bringing in a block in one go is that let's say we start with this address, then we in a high likelihood we'll access the next few addresses. So if a block, for example, contains the data of an array, so if we start from this address, very likely, very, very high likelihood we'll scan through the array, so we'll access all of these addresses. So this takes care of spatial locality as well. So now we have taken a look at both temporal locality as well as spatial locality. So next we will discuss how to use both of these and design our caches. So let me just summarize a couple of things, and caches we'll actually discuss in the next lecture. So what I want to summarize is I want to go back to the plots, right? One for temporal locality, one for spatial locality. So for temporal locality, we use the notion of the stack distance, and we said that if the stack distance is low, the temporal locality is high. And why was this the case? Because it's a standard pattern. We looked at a kitchen, we looked at Sophia's desk, we looked at a program with for loops. So since we access similar data, over and over again in a short period of time, it makes sense to actually have a cache hierarchy where you have a small and fast L1 which acts like a desk. So most accesses can be served by the L1. If you don't find it in L1, you have a larger L2 which acts like the shelf. And finally, you'll have the cabinet which will have all the addresses. And you don't find something in L1, you go to the main memory. So that's how essentially by creating a hierarchy of these caches, we are leveraging temporal locality and we're bringing this desk, shelf, and cabinet, this observation, this principle, into the design of processors as well. That's point number one. Point number two is that we plotted the address distance distribution, which measures the similarity in addresses, right, that the processor is accessing. We found that most of them are within plus or minus 20, 25, 30 bytes. So if we create an indivisible unit, so let's say if we fetch instead of 1 byte or 4 bytes at a time, we fetch let's say 64 bytes at a time, like fetching multiple vacation books at a time. If let's say I've started access in this address, most likely I'll access the addresses nearby, and all of them I would have already fetched because they're part of the same block. So we'll have a lot of cache hits, right? So we solve the problem of ensuring spatial locality by dividing the memory space into blocks. So that's also a very important concept. So to summarize, after this entire 1 hour lecture, we looked at a cache hierarchy, right? We justified it, and we divide memory into blocks. So these are our two important observations that we'll take forward when we actually design caches. All right, which is, I'm sorry, this slide.